So 3.4 is velocity and other rates of change. I don't know where these even came from. Hello? Write the area. Oh, okay. Oh, that is like literally the question. All right, so number 2. So these ones, it's kind of funny. Like these like first few problems don't really have instructions. I mean, they do, but like every problem's kind of different. So the instructions are just like the part A through D. So A, and when you're doing your problems, like you don't necessarily need to write out. I mean, I know you're not turning it in, but you don't necessarily need to write out the whole problem if you don't want to. It's up to you. But I'm going to write them out just for here so we can talk about them. Write the area A of a circle as a function of the circumference C. So we did something like this last year in pre-cal. We had a section in chapter 1 where we were like writing the area of a circle or whatever as like different things. But this one is as a function of circumference. So obviously area and circumference aren't really directly related, but they both have similar things, so I can solve and like get them to plug in. So the area of a circle obviously is pi r squared. Now I know that the circumference of a circle is 2 pi r. And so aside from pi, but the only variable that's in common in both of these equations is r. So basically I need to solve for r over here so that I have basically this formula as a function of circumference. Then I'm going to take that value that I end up with and plug it in for r over here. So we would have c divided by 2 pi is equal to r. And now I can take this part here and plug it in for r over here. Now, obviously, in area r is squared, so I'm going to have to square the whole thing. So I'm going to end up with a equals pi times c over 2 pi all squared. If you want to square it in one step, obviously that's also fine. So that would give me area is c squared times pi over 4 pi squared. And then to reduce it, I would end up with c squared over 4 pi. If I was just writing this as area equals whatever, I would probably leave it here. However, c is my variable, and I know that ultimately, just because of where we're at, it's going to want me to take the derivative of it. That's going to be part that's coming in a later section. So you may want to rewrite this as 1 over 4 pi, so that's like your constant value, times c squared, just for the sake of seeing it. If you're good with doing like when you had like x squared over 4 and you were taking the derivative, you could just leave it that way. But either of these would be acceptable for your area formula. Because B says to find the instantaneous rate of change. And sometimes I'll abbreviate rate of change like ROC, just so I don't have to write it out every time. So just FYI if you see me do that. Of the area A with respect to, which is what WRT is, circumference C. So basically this formula that I found in part A, to find instantaneous rate of change, we take the derivative of the function. So the derivative would be dA dC, because I'm taking the derivative of area with respect to circumference. So normally it's like dy dx, so it's kind of the same vibe. It's just we're using A and C here. is equal to, so when we take the derivative of this, c is what would normally be my x. So I put the 2 out front. Well, the 2 and the 4 are obviously going to reduce, so I'm going to end up with 1/2 pi times c. Or you could write it as c over 2 pi if you want to write it that way. It doesn't matter, obviously. It's the same thing either way. So anytime it's asking for instantaneous rate of change, you're basically just taking the derivative. It may give it to you at a particular point that you would plug in, which is what part C is about to do, but it may give it to you in a separate step like this one is doing. Because a lot of times it'll say, like with a actual like physics problem, it'll say find the instantaneous rate of change at time whatever. So C wants us to evaluate the rate of change of A at C equals pi and C equals 6 pi. So at C equals pi, I'm going to have dA dC is equal to, just plugging in pi for C, pi over 2 pi. Pi's obviously cancels, so that would be 1/2. And then at C equals 6 pi, dA dC is equal to 6 pi over 2 pi, which would be 3. So then the last part of this problem is basically giving us stuff about units. I'm not going to write out the whole thing on this one because it's just excessive. C is in inches and A is in inches squared. What units would be appropriate for dA dC? So basically, it's just inches squared over inches. Essentially, we just plug in the units, which would just mean that my final answer would be in inches. So nothing too crazy on those ones. All right, for a square of side length S is inscribed in a circle of radius R. So anytime they give me something like this, I mean, not that I don't look at what I'm ultimately trying to solve for in the other parts, but I usually like to draw a picture with something like this. So I've got my circle, I've got a square inside of my circle. We've got side length S on the square. The radius of the circle is R. And then obviously if I draw the whole diagonal of it, this one is also R over here. So I know obviously that that's a right angle. Knowing this information and that this is also a side, what do you know about this angle or these two angles here?
45, 45.
Yep, they're both 45 because that's a special triangle. So the area of a square is just side squared. And the area of a circle is pi r squared. So to kind of set this up, I need to figure out essentially an equation for the side, because what part A is going to tell me to do, and this is where you would need to kind of look at it beforehand, but I like to set all my stuff up before the problem. So write the area A of the square as a function of the radius r of the circle. So that means I can't have an s in my equation, basically. I've got to make it an r. So I need to figure out a way to rewrite this in terms of r. So I get rid of the s. So I need to solve it that way. So I can do a couple of things here. I can say that because I know this is 45, when I would solve a triangle, I could use a trig function, say like sine, and do opposite over hypotenuse of that, which would give me the sine of 45 is equal to s over, the hypotenuse is 2r. And then to solve for s, I can say, well, 2r times the sine of 45 is equal to s. So now I'll be able to plug this in here when I actually go to solve it in part A.
Could you try and do it like the Pythagorean theorem way? If like it's
S squared plus s squared equals 2r squared.
2r squared. Yeah.
Let's see. I don't know.
That's what I was thinking. I should really see if it would work.
Well, let me write it this way. 4r squared, so that way I've done that. So this would be 2s squared equals 4r squared. So then I would have divide by 4, so s squared over 2 equals r squared. So the square root of, let's see, it is going to work. I'm just trying to figure out how I want to write it. So this would be this square root of s squared over the square root of 2, which would just be s. So then that would be, and obviously I can't have a negative radius, so I'm ignoring the plus or minus part. S over the square root of 2, or s square root of 2 over 2, which the sine of 45 is root 2 over root 2. So 2r root 2 over 2. Actually, hold on. Wait, let me backtrack here. I messed up. I forgot. I need s by itself, not. So then I would have, s is equal to the square root of 2r, which would be the exact same thing I would get over here.
Okay.
Yeah. So, yeah, it would work. The other way you could potentially do it, if you remember stuff about special right triangle 45, 45, 90, is that the sides are 1, 1, root 2, which low-key probably would be the faster way to do it. But, yeah. I've never really thought to do it the Pythagorean theorem way, but that works. I mean, obviously that works too. So, yeah, either way would be fine to ultimately get us to that. And I actually like converting sine of 45 on over to square root of 2 over 2 first, because then that way I don't have to keep writing sine of 45 every time. Which obviously that's just a constant number, so when I take the derivative eventually, because I'm sure that's what I'm going to be doing in this problem, it'll just make it easier to not have to worry about that. So then part A, area A of the square as a function of radius. I'm just going to do that to abbreviate it. So that means that we can now write the area of my square as basically just the square root of 2 times r squared, which ends up just being 2r squared. Yeah, which makes this whole process faster because we went all the way down to there. So then B is instantaneous rate of change. Of the area with respect to radius. So then what would the derivative of this be then? Yep. dAdr is equal to 4r. Nice and easy. And so then part C, evaluate when r is equal to 1 or r is equal to 8. Well, obviously, pretty easy here. R equals 1, we have dAdr is equal to 4, because 4 times 1, and then when r is equal to 8, dAdr is equal to 4 times 8, which is 32. And then part D is the same thing about units. If r is in inches and a is in inches squared, what are the units of dAdr? Well, it's literally the exact same thing we had before, so just would be inches. Okay, so next thing, this might be where we pause after this problem. I'll just see. I don't remember if these next two go together or not. They do not. Okay. So number 8 is draining a tank. So basically, it says the number of gallons of water in a tank T minutes after the tank has started to drain is Q of T is equal to 200 times 30 minus T squared. How fast is the water running out at the end of 10 minutes? What is the average rate at which the water flows out during the first 10 minutes? So basically there's kind of like two parts to this question here. So just write down some pertinent information here. So we've got T is the minutes after tank is being drained, or like after it starts draining. Q is equal to 200 times 30 minus T squared, and it's 30 minus T, all that squared. And then they want to know how fast the water is running out at the end of 10 minutes. So that's kind of like my first part. So, because you don't know the chain rule yet, I kind of have two options here. I can use the definition of a derivative, or we could factor and take the derivative, because ultimately that's what I need to be able to solve. I'm going to show it with the definition just so that you can see it, because obviously the definition works in all cases. So they want to know after the first 10 minutes. So the formula, I was going to see if they actually write it in this section for rate of change. I feel like they probably do somewhere. Let me look. Yeah, they do. So let me just write it just for reference. So we have V of t is equal to ds dt, which is the limit as t approaches 0, or delta t approaches 0, of f of t plus delta t minus f of t all over delta t. So basically here what's happening is I am plugging in the values for what I'm given. So delta T in this sense is going to be 10. Or well, it's going to end up being like 10 on the top, and we can use that method to do it. So I'm going to end up with, if I use this, the limit as delta T approaches 0. Oh, actually, I don't need this until part B. Hold on. Scratch that. I need this for part B. I'm looking at the wrong thing. For how fast the water's running out after 10 minutes, I'm just going to take the derivative. I mean, this is for during the first 10 minutes, which is what second part asking. What is the average rate at which the water flows out during the first 10 minutes? This is what I'm going to need for that. So hold on. That's going to end up being used for part B. Okay, so part A, I do need to factor this then. And so this would be Q is equal to 200 times 900 minus 60T plus T squared. So then I've got 180,000, I think, yeah, minus 12,000 T plus 200 T squared. Yeah, so that's still Q. And then I can take the derivative and solve, and it'll be way faster. So Q prime of T then would be what?
Negative 12,000 and 2T plus 2T. Oh, 200T. Oops. Right, put the 200.
So 400T then, yeah. Just need 2 more zeros. So then now I can take this and evaluate it. It wants it specifically at the end of 10 minutes, so that just means I need to plug in 10. So Q prime of 10 is negative 12,000 plus 400 times 10. And so that's going to give me negative 8,000, which means that it is, because it's asking, the reason the number is negative is because it's running out. So we would say it's running out at 8,000 gallons per minute, which is insane.
That is wild.
Also, like, how big is this tank?
That's what I was thinking too.
That it's 8,000 gallons in, like, per minute.
Yeah, we're going for 10 minutes, so.
That's crazy. Okay, so yeah, if we're using instantaneous, which is if it's at a specific point in time, which is what this was, we're just taking the derivative and evaluating it at the value. This equation that I gave us is for average rate of change, which is over a period of time. So part B was asking me for average rate of change during the first 10 minutes. So part B, AROC is my average rate of change during the first 10 minutes. So that means as on an interval from 0 to 10, which means delta T is equal to 10. So that's what I was trying to fill in earlier, and then that's when I realized, oh no, that means over a period of time. So now is where I'm going to use this formula, basically, that I had plugged in here. So T plus delta T, basically, that's like 0 plus 10. So essentially when I plug this in, all I really need is like over the time what's happening. So one of them's going to be 10 and one of them's going to be 0 because it's over the first 10 minutes. So this is going to be 200, and I'm actually really plugging everything in, so there's not anything that's going to end up being the limit of. So, 200, not 2,000, times 30 minus 10 squared minus 200 times 30 minus 0 squared. So it's like your final minus initial. So it's a little bit of a modification kind of that first formula that I gave you. Just because if the other formula would be more like if it said from like 5 minutes to 15 minutes, we'd have to shift it a little bit because it could change as time goes on. It may be running out more or may not be running out as much. So that's why we have the first formula. But since this is just in the first 10 minutes, we don't have to worry about that. And then over 10 squared, which is my delta t. So then that's just 20 squared, which is 400. So I've got 200 times 400 minus 200 times 900 over 100. So then 80,000 minus 18,000, nope, 180,000, there we go, over 100. So then that's negative 100,000. Hold on a second. Oh, wait. Hold on. I don't think that's actually supposed to be squared. Because it's just delta t on the bottom. Where? Yeah, it's not supposed to be squared, so hold on. Let me change this. Then over 10. So then one of the zeros just cancels off. So this is negative 10,000 gallons per minute. Or, well, obviously that it's running out, which is what the negative is telling us. So the average velocity is 10,000 gallons per minute running out. So anyways, okay, so we will stop there for today. We'll probably wrap up tomorrow. I think we should be able to finish it tomorrow, but we'll have to look at like the graph. Like if you remember looking at a couple of the little particle motion graphs in physics, like we're kind of doing that, but now with calculus. But we've only got a couple problems left to look at, so it shouldn't take us too long.